Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue our discussion on acids and bases, and we are nearly done with the topic. I think this stream and maybe one more stream next week and we'll have this topic completely wrapped up. So if you've been following along this whole time, I could totally understand if you're sick of hearing about acids and bases. To be honest, I'm a little bit sick of talking about acids and bases. However, I do believe it is very important to finish what we start. Finish the topic of acids and bases. And so to that end, I present to you Acids and Bases Volume 8. So I'm going to move myself over here briefly. So as usual, your feedback is more than welcome and highly encouraged. So please, if you're watching this live, feel free to drop your thoughts in the chat. And if you're watching this as a video, please leave me a comment. Without your feedback, I am lost. This video and all of the videos that preceded it that are related to acids and bases are all compiled together into a playlist called Acids and Bases Live Streams. There's a link right down in the description if you're interested in watching any of my other acids and bases content. All right, so let's go ahead and get into the content. So we're going to start by briefly reviewing last week's material. That was Volume 7. So Acids and Bases Volume 7. What did we talk about? Well, we talked a lot about bases. So leading up until then, we talked a lot about acid, strong acid, weak acid, pH of an acid, all that kind of stuff, polyprotic acids, percent ionization of an acid. But last week, we talked all about bases. And just as acids can be categorized into strong and weak, so too can bases be categorized into strong bases and weak bases. So we talked about strong bases, the general formula of a strong base behaving as a base in water is shown here, where you have a metal hydroxide, usually a group 1A or group 2A metal hydroxide, reacting to form the metal cation and the hydroxide ion. So the production of hydroxide ions is what defines this as a base. So this is what the strong base chemical equation would look like. And of course, finding the pH of a strong base solution is very, very straightforward because a complete ionization takes place. All of that initial concentration of metal hydroxide has been converted into the metal cation and hydroxide. And so we saw an example, a couple of examples of calculating a pH of a strong base solution in the previous live stream. And then we also talked about weak bases. And so we started to see even more parallels between acids and bases, because just as a weak acid can be quantified using the acid ionization constant, or Ka, a weak base can also be quantified using an equilibrium constant that we call the base dissociation constant, or the base ionization constant. So in general, this would be the formula here of a weak base reacting with water, where you have the base taking a proton from water, the water acting as an acid, donating a proton to the base, and the base is like, hey, thanks for that proton, thanks for that H+, to result in the conjugate acid of the base, shown here as BH+, and hydroxide ion. So the equilibrium constant for that process is, just as any equilibrium constant, is the products over the reactants. So here it would be BH+ and OH-, those two concentrations, divided by the concentration of the base. Of course, we ignore water. We omit it from the equilibrium constant expression because water is a pure liquid. Pure solids and liquids, their concentrations do not change throughout the course of a reaction, and so they do not appear in equilibrium constant expression. So just as Ka describes the extent of a reaction of a weak acid, Kb describes the extent of a reaction of a weak base reacting with water. So this is what it would look like. So this is just a couple of examples of some common weak bases that we looked at. Their names, their formulas, the conjugate acids of those weak bases, and also their Kb values, their base dissociation constant values. And I also included a column over here for the pKb. So just as the P scale can be applied to Ka, pKa, it can be applied to hydronium concentration, pH or pOH or whatever. We can also apply that to the Kb property, where the pKb is simply equal to the negative logarithm of Kb. And so that makes the numbers a little bit easier on the eyes. It's much easier to compare these pKb numbers right here that don't have scientific notation to all of these Kb values over here that do have scientific notation. So weak acids, weak bases. And then the last thing we did last week was we found the pH of a weak base solution. So we basically applied the same techniques that we've been using this entire time. If you have the initial concentration of the weak base and you know the Kb for that weak base, you can basically perform an equilibrium type problem where you write the chemical equation, construct an ICE table, use that to build a quadratic equation, solve the quadratic equation, and then insert those values into the formula for POH or pH, and that gives you the answer to your problem. So that was last week, so it's time to move on and discuss the topic of tonight's stream. So tonight, what we're going to be talking about is the acid-base properties of ions and salts, right? So an ion, of course, is an atom or a collection of atoms that has an overall charge, positive or negative. If it's positive, we call it a cation. If it's negative, we call it an anion. And a salt is simply an ionic compound, a collection of cations and anions joined together by ionic bonds. So I'd like you to imagine the following situation. So let's say we have a sample of sodium bicarbonate, which is given by the formula NaHCO3. It's also called baking soda. You may know it by that name. So let's say I have some sodium bicarbonate and I dissolve it in water. Sodium bicarbonate is a soluble salt. Not all salts are soluble, but sodium bicarbonate is a soluble salt. So if you put it in water, it will dissolve. And I want to know that solution of sodium bicarbonate, is it acidic, is it basic, or is it neutral? Is there any way I can figure that out? Is there any way that I could figure out what I should expect the acidity or basicity of this solution to be? Should it be acidic, basic, or neutral? So that is the question. Now, in the case of sodium bicarbonate, basically these two equations over here describe what happens, right? So the first equation, this one up here, describes the dissociation of sodium bicarbonate into sodium ion and bicarbonate ion, and this will always be true for a soluble salt, right? If the salt is soluble in water, it will dissociate into its constituent ions, in this case, sodium ion and bicarbonate ion. And then shortly thereafter, the bicarbonate ion acts as a base. It actually strips a proton from water to yield carbonic acid, that's H2CO3, and the hydroxide ion, OH-. And so if we have a sodium bicarbonate solution, and we know that these two processes are happening, right? The sodium bicarbonate dissociates, and then following that, you have the bicarbonate ion acting as a base. Well, we would expect the pH in this case to be greater than 7. We would expect this to be a basic solution. Why? Because the anion of our salt is behaving as a base. Now you might be asking yourself, well, what about the sodium ion? Does the sodium ion act as an acid? The answer is no. The sodium ion is neutral, and the bicarbonate ion is acting as a base. So why does the bicarbonate ion act as a base, and why is the sodium ion neutral? These are some of the questions that we are going to address in this stream. So let's start by talking about anions and how anions can behave as weak bases. Not all anions, and remember, anions, that's just a negatively charged ion, right? Not all anions can behave as a base, but some of them can. And so we're going to learn how to differentiate between which ones can and which ones cannot behave as a base. And the important thing to understand about anions is that any anion can be considered the conjugate base of an acid, right? So if I have the bicarbonate ion, as we've just seen, you can consider that the conjugate base of carbonic acid, H2CO3. If I have the chloride ion, Cl-, well, that would be the conjugate base of HCl. F-, that would be the conjugate base of HF. If I have the acetate ion, C2H3O2-, well, that's the conjugate base of acetic acid, HC2H3O2, right? So remember, any anion can be considered the conjugate base of an acid, right? Now, this following slide here, this is where it starts to get pretty interesting. So I've constructed this little flow chart here. So basically, if you take a look at your anion, and your anion happens to be the conjugate base of a weak acid, then that anion itself will act as a weak base. If, however, the anion is the conjugate base of a strong acid, then that anion does not act as a base. It doesn't act as an acid either, but it doesn't act as a base. It is pH neutral. So in the previous example with sodium bicarbonate, the bicarbonate ion happens to be the conjugate base of a weak acid. Carbonic acid is a weak acid, and so therefore the bicarbonate ion acts as a weak base. So that's how you know whether your anion is weakly basic or pH neutral. It all depends on what type of acid, strong or weak, that anion is the conjugate base of. Okay, so, and it looks like I haven't really given myself much room on this slide to put myself. Let's see if I could just squeeze myself down here, try to get out of the way of all this information. So this is a slide that we actually looked at some time ago in a previous live stream. And this slide basically tries to explain the origin of acid strength, right? So if we're talking about just a generic acid reacting with water, you have this general formula up here: HA plus H2O yields H3O plus and A minus, the conjugate base of the acid HA. And of course, the reactants and products are separated by either a single-headed arrow, if we have a strong acid, indicating a complete ionization, or they're separated by these equilibrium arrows, which indicate a partial ionization. That would be a weak acid, right? Now, the origin of acid strength all depends on the interaction, the attractive force between the conjugate base, which according to this formula we're calling A minus, and H plus. So it's all about the interaction between the conjugate base and H plus. If that interaction between the conjugate base and H plus is a weak attraction, then you have a strong acid, right? So if you had like HCl or something like that, that means that the conjugate base of that acid, the attraction between that conjugate base and H plus is very, very weak. And so that's why you get a complete ionization in the case of a strong acid. And on the other hand, if you have a weak acid, that means that there's a fairly strong interaction between the conjugate base and H plus. And so that results in a partial ionization. And so we can see here how it kind of makes sense that an anion, which is the conjugate base of a weak acid, is itself a weak base, because by definition, if it's the conjugate base of a weak acid, then that means it's fairly strongly attracted to H plus, and so it's going to strip H pluses off of a water to behave as a base. So, all right, so we're going to move on to this slide here. This is just a couple of problems that we're going to look at, or you can consider it like a three-part problem. So this says to determine whether each of the following anions is a weak base or pH neutral. We have Br minus, that's the bromide ion. We have NO2 minus, that's the nitrite ion. And then ClO minus, that's the hypochlorite ion. So I'm going to take you to the whiteboard real quick. So we're going to the whiteboard. I'm just going to copy and paste this problem. So bear with me here while I copy and paste this problem to the whiteboard. By the way, if you find this stream valuable, I would appreciate your giving a thumbs up on this live stream or video, depending on whichever you are watching. Maybe share it with people who might be interested. Supporting the stream however you can. I would wholeheartedly appreciate your support. All right, so we're going back to the whiteboard here. Got my problem pasted in. Gonna enlarge it so that we can see everything. Okay. So we are asked to determine whether each of the following anions is a weak base or pH neutral. Well, if we look at the first one, that's the bromide ion, right? So the bromide ion is the conjugate base of what acid? Well, that would be HBr. Remember, a conjugate acid-base pair, those are just two substances that are related by the transfer of an H+. So if we add an H+ to Br, we get HBr. So Br minus is the conjugate base of HBr. So the question that we're really asking ourselves is HBr, is that a strong acid or is it a weak acid? If we look at a table of strong acids, are we going to find HBr in there? If we look at a table of weak acids, are we going to find HBr in there? And this isn't a rhetorical question. Anybody who's watching right now, I invite you to speak up. Speak up. Let your voice be heard in the chat. Let me know if HBr is a strong acid or a weak acid. Doesn't look like I'm getting any responses, so I'll go ahead and just tell you right now that this is a strong acid. Strong acid, HBr, right? And if your anion, right, is the conjugate base of a strong acid, then it will be neutral. It will not be basic, right? So again, if your anion is the conjugate base of a strong acid, then that anion is pH neutral. Now, if we have NO2 minus, this is the next example, NO2 minus, that's the conjugate base of which acid? That would be HNO2. And that's called nitrous acid, HNO2. So the question again is, HNO2 a strong acid or a weak acid? And if you look up in your reference tables of your chemistry textbook, you will find that HNO2 is a weak acid. And therefore, our anion, since it is the conjugate base of a weak acid, our anion is going to behave as a weak base. Because our anion is the conjugate base of a weak acid, it's a weak base. So let's go to this other example here. We have ClO minus, that's the hypochlorite ion. So it's the conjugate base of which acid? That would be HClO. That would be hypochlorous acid. Hypochlorous acid happens to be a weak acid. And therefore, our anion, ClO minus, since it's the conjugate base of a weak acid, it is going to be a weak base. So really, all these problems is just being able to tell if an acid is a strong acid or a weak acid, which you should know upon repeated exposure to problems like these. And then just understanding that relationship where if the anion is the conjugate base of a strong acid, then it's pH neutral. If the anion is the conjugate base of a weak acid, then it's going to be a weakly basic anion, right? So I think that's pretty straightforward. So we're going to move on here and go to the next thing. I'm just going to pull up my PowerPoints real quick just to see where we are. Okay, so the next thing I'm going to do, I'm actually going to keep it right here in the whiteboard, but I'm going to paste something else in here we can sort of use the whiteboard. I'm going to do like this whiteboard style lecture for this next part. So I'm really excited about it here. So okay, so we understand that an anion is going to be either weakly basic or pH neutral, depending on the strength of the conjugate acid of that anion, right? So now, what if we wanted to get more specific? In other words, what if we wanted to actually numerically quantify the acidity or basicity of a solution containing an anion acting as a base? So in other words, what if I wanted to find the pH of a solution with an anion in it that's acting as a base? Well, remember, if you're trying to figure out the pH of a weak base solution, all you really need are two things. You need the initial concentration, which I'll just put as like this, like concentration of B, the initial concentration of the base, and you also need Kb. You need the base ionization constant. So these are the two things that you need in order to find the pH of a weak base solution, right? You would write the equation, construct your ice table, build a quadratic equation, solve it, blah, 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 all the stuff that we've been doing over and over again over the course of this live stream series, right? Now, but what if we don't know Kb, right? What if we don't know Kb, but what if we do know Ka of the conjugate acid? So is there any relationship between Ka of the conjugate acid of our base, right? Is there any relationship between Ka, the conjugate acid of our base, and Kb? And it turns out there is. So what we're going to do is we're going to sort of derive that equation real quick. So if I have, let's say, any general weak acid, right? And I'll call that acid HA, right? And that's aqueous. And it's reacting with water, then it's going to react with water according to this equation where we have HA, the acid, reacting with water, which is a liquid. Going to use the half-headed equilibrium arrows, which are very poorly drawn. Let me take another stab at that. It's a little bit better. To produce H3O plus, and that's also aqueous. And we're also going to get a minus, right? And that's aqueous, right? So that's the formula associated with a weak acid reacting with water. Now, let's say we're talking about A minus, and let's assume that A minus, this anion, acts as a base, right? So what would that equation look like? Well, that would look like this, where we have A minus, right? And that's aqueous reacting with water, right? A minus reacting with water to produce HA, the conjugate acid of that anion, aqueous, and that's going to be plus the hydroxide ion, OH minus, right? So these two equations describe basically what's happening where you have a weak acid reacting to form a base, or the conjugate acid of it, or excuse me, the conjugate base of it, and then that anion acting as a base. So let's see if we can write the expressions for Ka associated with this process and Kb associated with this process. So I'm going to do this in purple, right? So if I have Ka for this process up here, right, what is that going to be equal to? Well, it's an equilibrium, so it's going to be products over reactants, right? So in this case, that's H3O plus concentration of hydronium times concentration of A minus. Those are the products divided by the reactants. We're going to have HA, and we're going to ignore the water for reasons that I explained earlier on in this live stream. So that's the expression for Ka. And then for Kb, I'm going to minimize myself a little bit here so I can give myself a little bit more room to write the expression for Kb according to this equation down here, right? So Kb would be concentration of HA times concentration of hydroxide ion divided by concentration of A minus, right? So this would be the expression for Kb. Now, I want to show you guys something fairly interesting here. And let's see if I can scroll or drag this stuff up so I can get some more room here. So what if I wanted to, let's say, multiply Ka. What am I doing here? Why did it change back on me? Sorry about that, guys. Okay, maybe I can just, yeah, I can just do that. There we go. Okay, so what if I wanted to multiply Ka and Kb, right? If I wanted to multiply Ka and Kb, what would that look like? Well, I'll go ahead and drag the expression for Ka over here, and I'll put some parentheses around it since I'm multiplying it, right? And then I'll do the same thing with this Kb. I'll drag that, and I'll multiplying these two together. I'll put some parentheses around that too. And then notice that some things in this expression, Ka times Kb, start to cancel, right? A minus cancels with A minus. HA cancels with HA. So that what we're left with is the product of Ka and Kb is simply the hydronium concentration, that's H3O plus, times the hydroxide concentration, OH minus. Now, there's another property of acidic solutions, or acidic or basic solutions, aqueous solutions, that is given by this expression right here, H3O plus times OH minus. Can anybody remember what value, what constant that is called, or what constant is described by this expression right here? Well, that, folks, happens to be Kw. So I just realized I'm off the page here again, so let me scroll up here. Okay, so this is Kw, and it looks like we already got a response in the chat from Elvira. Yes, that's correct. It is Kw, right? I just wrote Ka because I'm not very smart. Kw. I'm inviting you guys to help me when I make a mistake here, because I'm certainly not perfect. So we have just derived a very, very important relationship between Ka and Kb, which is that the product, I'll do this in red, the product of Ka and Kb is equal to Kw. And Elvira also pointed out in the chat, thank you for your participation, Elvira, appreciate it, that the value of Kw is 1.0 times 10 to the minus 14. So it's 1.0 times 10 to the minus 14. Now, of course, that's assuming that the reaction is taking place at 25 degrees Celsius, which is like the most commonly reported temperature in chemistry textbooks, right? So Ka times Kb is equal to Kw at 25 degrees. That value of Kw is 1.0 times 10 to the minus 14. So what this means is that if we don't know Kb, but we do know Ka for the conjugate acid of that base, right, that anion, then we can simply take that Ka value and divide 1.0 times 10 to the minus 14 by it, right? Take 1.0 times 10 to the minus 14, divide it by that value of Ka, and that'll get you your Kb, and that will help you find the pH of your solution that contains an anion acting as a weak base. So if that sounds confusing, please let me know. I can re-explain it or try to explain it a better way, but that's basically the strategy here, right? So the formula that I want to highlight here, I know this is a lot of text on the screen here, is this right here. The product of Ka and Kb is equal to Kw, which is equal to 1.0 times 10 to the minus 14 if you are at 25 degrees Celsius. So now that we understand that relationship, Ka times Kb equals Kw, we're in a pretty good position where we can actually find the pH of a solution containing an anion acting as a weak base. So I'm going to paste another problem in here, if you guys will give me just a moment. So this is a problem that I have. By the way, this is my first time solving the problem. I just wrote the problem, but I haven't actually solved the problem. Usually I solve these things and I have like a cheat sheet that I can kind of look off of if I get stuck. But this is my first time solving this. So I guess what I'm trying to say is I'm inviting you to follow along and solve this with me, because there's a chance I might get something wrong because I have like live stream jitters and stage fright or whatever is going on. Okay. So this problem says to calculate the pH of a 0.331 molar solution of sodium acetate, that's NaC2H3O2, 0.331 molar sodium acetate solution, and it says that the Ka value of acetic acid is 1.7 times 10 to the minus 5. Okay, so this is interesting, right? So we have our initial concentration of acetic acid, right? The sodium ion, right? So when sodium acetate dissolves in water, it's going to split up into sodium ion and acetate ion. The sodium ion is actually inert for reasons that we're going to discuss in the future, but the acetate ion acts as a weak base. So there are two things we need. We need the initial concentration, which we have, which was given by the problem, and we also need Kb, but we don't have Kb, we have Ka. So we're going to use that handy-dandy relationship where the product of Ka and Kb is equal to Kw to get Kb, and then we can simply use that value and carry on as we normally would in an equilibrium acid-base type problem. Okay, so the first thing I'm going to do is I'm going to try to find my Kb, right? So Kb, that is going to be 1.0 times 10 to the minus 14 divided by Ka, right? Now Ka of acetic acid, that was given to us as 1.7 times 10 to the minus 5. So we have 1.0 times 10 to the minus 14 divided by 1.7 times 10 to the minus 5. So I'm going to go ahead and calculate this real quick. 10 to the minus 14 divided by 1.7 times 10 to the minus 5. The value of Kb that I got is 5.9 times 10 to the minus 10. 5.9 times 10 to the minus. So what I'm going to do is I'm just going to erase. What am I going to do? I'm going to erase. I guess I need the pen to do this. Hang on. I'm going to erase all that and just sort of lasso this in and drag it over here. Come on. So Kb is equal to 5.9 times 10 to the minus 10. So we're going to continue this as though it was any equilibrium acid-base problem. So the first thing that we're going to do is to write the equation for the weak base reacting with water. In this case, the weak base is our acetate ion. So that's, I guess I'll do that down here. So we have C2H3O2 H3O2 minus aqueous reacting with water, H2O, that's a liquid, and that's going to react to produce acetic acid, that's HC2H3O2 aqueous, and the hydroxide ion, that's OH minus, also aqueous, right? So the next thing we can do is we can construct an ICE table. So ICE, that's initial change equilibrium. The problem tells us that initially we have 0.331 molar acetate ion, right? We had 0.331 molar sodium acetate, so that means we have 0.331 molar acetate ion. We can safely assume that the concentrations of acetic acid and hydroxide ion are 0 prior to the start of this reaction. The change, well, it's going to be minus X for the acetate ion. It's going to be plus X for the acetic acid and plus X for the hydroxide ion. And I know I'm going through this kind of quickly, but I'm going through it quickly because I'm assuming that we've done this already, because I've done it in my live streams time and time and time again. I'm just going through it for the sake of completion. So DT Jane says it's 7 a.m. in India. Cool. Well, it's 9:30 p.m. over here in the eastern United States. So thank you for joining, and I guess good morning. Good evening to everybody who's closer to my end of the globe. All right, so at equilibrium, we're going to have 0.331 minus X for the acetate ion, and then for acetic acid and hydroxide, those are each just going to be X. And so this is what's going to help us build our quadratic equation here, right? So we know that KB, hopefully I have enough room here. I don't know how much room I've given myself. So KB, we know that is, the expression for that is going to be concentration of acetate ion, that's HC2H3O2 times OH minus, right? This is just the equilibrium constant expression for KB. I'm just putting it in here just so there's no confusion. Divided by acetate ion, that's C2H3O2 minus, right? So we know that KB, which is equal to this long-winded expression here, which is also equal to 5.9 times 10 to the minus 10, which we calculated earlier, is equal to, and now we can start to substitute our equilibrium concentrations in terms of X into this expression up here. So in the numerator, what do we have? Well, we have X times X, which we can write simply as X squared. In the denominator, we have 0.331 minus X. That's the equilibrium concentration of acetate ion. We can use the X is small approximation here and assume that this value of X is very, very small compared to the number from which we are subtracting it, which is 0.331. It's the X is small approximation. Again, we've done this several times before in this live stream playlist. So I'm going to assume that that's really, really small and just kind of delete it, just kind of pretend it's not there. And so what are we left with? I'm just going to go ahead and erase a lot of this stuff because we're done with it, right? So I'm just going to erase that. I apologize if you needed that. You can always rewind it, I suppose, if you wanted to. So I'm just going to lasso this up and bring it closer to the middle of the screen here, right? So we're left with this equation over here. X squared over 0.331 is equal to 5.9 times 10 to the minus 10. What we're going to do is we're going to multiply both sides of the equation by 0.331. So 0.331, we're going to multiply that. And then once we do that on the right-hand side of the equation, it gets rid of it in the denominator. So what we're left with is X squared is equal to the product of 0.331 and 5.9 times 10 to the minus 10. Now we just have to get rid of this squared over here and this X squared. And so to do that, we're going to take the square root of both sides of the equation. And the square root of X squared, of course, is simply X. And so for the value of X, which is equal to the hydroxide concentration, right? X is equal to the hydroxide ion concentration. That's going to be equal to the square root of the product of 0.331 and 5.9 times 10 to the minus 10. Everybody still following me? I know I'm going through this stuff quickly, but again, that's only because we've done this similar technique many times before, and I just don't want to spend too much time on it. So I'm going to go ahead and punch this into my calculator. If anybody else wants to participate, you are more than welcome and highly encouraged to do so. I'm going to put this in my calculator. So square root of the product of 0.331 and 5.9 times 10 to the minus 10. The value that I got, and I'm going to put this in scientific notation, the value that I got is, how many sig figs am I going to put in here? I guess just 2. 1.4 times 10 to the minus 5 molar, right? Our hydroxide concentration is 1.4 times 10 to the minus 5 molar. So I'm just going to grab this guy and stick it up here. So that's hydroxide concentration, but we're still kind of a long way from finding pH. Well, we can find pOH, right? pOH, that's the negative logarithm of the hydroxide concentration. So in this case, negative log of 1.4 times 10 to the minus 5, right? Negative log of 1.4 times 10 to the minus 5. Let me punch that in my calculator real quick. Let's see, negative logarithm of 1.4 times 10 to the minus 5. So this is pOH. What I got was 4.85. So pOH equals 4.85, right? And we understand from a previous stream, because I know everybody who's watching this now has completely followed along and watched all of my live streams in the playlist, right? We know that the sum of pH and pOH is equal to 14, right? So since we have pOH and we're looking for pH, all we need to do at this point is to subtract the pOH value that we have from 14, and that gives us pH. So pH is equal to 14 minus the pOH, which is 4.85. So pH is 14 minus 4.85, and so what would that be? 9.15, I think. Let me punch it in a calculator just because I don't want to humiliate myself live on the internet here. 14 minus 4.85. My mental math sucks. I'm just going to admit it. My mental math is horrible. So yeah, 9.15. So really, most of that problem was stuff that we've already done before. The one sort of extra thing that we had to do was to understand that the product of Ka and Kb is equal to Kw. And so if we have Ka and we need Kb, all we have to do is apply that relationship, divide Kw 1.0 times 10 to the minus 14 by our given Ka to get our Kb, and then we just plug that Kb in and do an equilibrium problem, just as we've done time and time again. Okay, so we've just talked a lot about anions that behave as weak bases. And so we're going to go back to the PowerPoint. We spent a lot of time on the whiteboard. Now we're going to go back to the PowerPoint here. And so now we're going to switch gears and we're going to talk about cations, right? We've talked about how anions can act as weak bases. Cations can actually act as weak acids. Cations fall into two categories. They either act as weak acids or they are pH neutral. Remember, a cation, that's a positively charged ion, right? And cations tend to fall into three different categories. So the three categories are as follows. You have cations that are counter ions of strong bases. So counter ion of a strong base, that just means the cation that is paired up with hydroxide in a strong base. So like sodium ion would be the counter ion of hydroxide because sodium hydroxide is a strong base, and so on. Then you have the second category, which is cations that are the conjugate acids of weak bases. And then finally, you have cations that are small, highly charged metals. So we're going to examine each of these categories individually, starting with cations that are the counter ions of strong bases, right? So if you consider these cations here, sodium ion, lithium ion, calcium ion, what do all of these cations have in common? They are all counter ions of strong bases, right? Sodium ion, that's the counter ion of sodium hydroxide. Lithium ion, that's the counter ion of lithium hydroxide. Calcium ion, that's the counter counter ion of calcium hydroxide. All of these group 1A metal, group 2A metal cations are counter ions of strong bases, and all of these are pH neutral, right? They do not react with water to produce more hydronium ion, right? So Elvira says, what qualifies a cation to be neutral? Good question. So if your cation is the counter ion of a strong base, then it is neutral. So in other words, any group 1A metal or group 2A metal cation, alkali metal or alkaline earth metal cation, is pH neutral. It does not ionize water. So we're going to move on and talk about the second category, and these are cations that are the conjugate bases of, the conjugate acids of weak bases. So there's a couple more cations that we can see here, like NH4+. That's called the ammonium ion, right? That's the conjugate acid of the base NH3, ammonia, right? This cation here, CH3NH3+, that's the conjugate acid of this base here, this base CH3NH2, that's called methylamine. You might be familiar with it from a TV show called Breaking Bad, which is a phenomenal show. If you've never seen it, I highly recommend watching it. It's pretty awesome. There's another one down here, C5H5NH+. That's the conjugate acid of, there shouldn't be an H plus over here. I just messed that one up, so let me change that real quick. There we go. All right, so I'm going to go back to reading. Okay, so C5H5NH+, that is the conjugate acid of this base here, C5H5N, which is called pyridine. And so any cation that is the conjugate acid of a weak base is itself going to react with water as an acid. It's going to donate a proton to water to form hydronium ion and the base. And that means that it's behaving as a weak base, weak acid. Should have said acid here. Man, I really need to proofread these things. You know, I do proofread them, but like I just don't catch everything. So I apologize, everybody, for the confusion. So yeah, so a cation that is the conjugate acid of a weak base is itself a weak acid. So that's important to understand. And then the third category has to do with cations that are small, highly charged metals. So what does that mean? Well, if you have a small, highly charged metal like aluminum, right? So if you have like an Al3+ cation, right? That actually reacts with water and it becomes hydrated. So one aluminum ion can actually collect 6 water molecules to form this species right here, Al-H2O in parentheses 6 with a charge of 3+. And then this species here, this whole thing, this Al with 6 waters on it and a charge of 3+, that actually reacts with water. It donates a proton to a water and it acts as a weak acid itself. So if you have a small, highly charged metal like an aluminum ion, or maybe iron 3+, the ferric ion, Fe3+, or if you have like chromium, a lot of those transition metals would fall into this category here. But this does not apply to alkali metals or alkaline earth metal cations. So that would be the third category of cations, right? So really, if you have a salt solution, so if you have any salt, any ionic compound, and you dissolve it in water, and you want to know whether that solution is going to be acidic, basic, or neutral, right? There's really only 4 possibilities. Either you have a neutral cation and a neutral anion, an acidic cation and a neutral anion, a neutral cation and a basic anion, or you have an acidic cation and a basic anion. And so let's go through all of these situations individually, and we'll see if we can predict what these types of solutions would be in terms of whether they'd be acidic, basic, or neutral. So I'm going to take you guys to the whiteboard here, and I'm just going to grab the images that were just shown on that PowerPoint slide, and we're going to take a look at this. So, okay, so we're going to examine each of these 4 possibilities individually and try to make sense of it all, so to speak. So, The first possibility is neutral cation, neutral anion, right? So let's say your cation, right, is the conjugate acid of a strong base, right? And let's say that, or the counter ion of a strong base. And let's say that your anion is the conjugate base of a strong acid. So in that case, you'd have a neutral cation and a neutral anion. And if your cation and anion are both neutral, then your solution is going to be neutral. So that's pretty straightforward. That's kind of the easiest of the four possibilities. This possibility over here, if we have an acidic cation and a neutral anion, well, if you have the cation behaving as an acid, but your anion isn't behaving as a base, well, then that means you're going to have an acidic solution, right? Over here, if you have a neutral cation and a basic anion, well, your anion's acting as a base, but your cation's not doing anything. That means you're going to have a basic solution, right? Yes, that's right. And finally, if you have an acidic cation and a basic anion, well, does your solution end up being acidic, basic, or neutral? And this one depends, right? I'm just going to write the word depends. So what does it depend on? Well, if your cation is acidic and your anion is basic, what it really depends on are the relative values of Ka for the acidic reaction and Kb for the reaction of the base reacting with water. If the Ka for your acid is larger than the Kb for your base, then you'll have an acidic solution. If the Kb for your base is larger than the Ka for your acid, then you'll have a basic solution. And so you just have to figure out what those numbers are, and then you can compare them, see which one's larger. The larger of the two will dominate and determine whether you have an overall acidic, basic, or neutral solution. So let's go through a couple of examples before we have everything wrapped up for the night. I'm going to get back into the PowerPoint here. So I think I'm just going to copy something from the PowerPoint and just paste it over into the whiteboard. Yep, looks like I can do that. So copy this, and then I'm just going to delete everything here. And then we are going to just look at a few examples of some ionic compounds, some salts, and predict whether these salts, when dissolved in water, would result in an acidic solution, a basic solution, or a neutral solution. So we have CaCl2, we have AlCl3, we have NaHCO2, and we have NH4F. Okay, so we'll go through each of them individually, right? So with CaCl2, well, our cation in this case is Ca2+. Our anion is Cl-. Yes, we have two of them, but that doesn't really make much of a difference here, trying to figure out whether the anion behaves as a base or neutral, right? So the cation's either going to be acidic or neutral, and the anion is either going to be basic or neutral, right? Ca2+, so is that the conjugate acid of a weak base, or is that the counter ion of a strong base, or is it a small, highly charged metal? Well, it turns out that Ca2+, calcium ion, is the counter ion of a strong base, calcium hydroxide. Calcium hydroxide is a small base. Calcium ion, being the counter ion of a strong base, is going to be a neutral cation. So it's not going to ionize water to behave as an acid. And if you have Cl-, well, Cl-, right, is that the conjugate base of a strong acid or the conjugate base of a weak acid? Well, Cl-, that's the conjugate base of a strong acid, right? HCl, that's a strong acid. So if you have your anion, which is the conjugate base of a strong acid, then that's also going to be neutral, right? And since we have a neutral cation with a neutral anion, our solution will overall be neutral. Okay, so I'll just create a solution column over here. So we have cation, anion, and then solution, right? So this next one, AlCl3, right? Well, in this case, our anion, that's Al3+, and that's our cation. Our anion is Cl-. Al3+, well, is that the counter ion of a strong base? Is that the conjugate acid of a weak base, or is it a small, highly charged metal? This one, like we just saw in the previous slide, is a small, highly charged metal. And so this one is going to behave as a weak acid. Now the chloride ion, well, we just kind of talked about this one in the previous example, right? Since chloride is the conjugate base of a strong acid, chloride ion is neutral, right? So since we have a weakly acidic cation and a neutral anion, that means we're going to have an acidic solution, right? We're going to have a solution in which the pH is lower than 7. This next one, going right along, we have Na+, that's our cation, so I'm going to write that down. So we have sodium formate, that's what this is called, sodium formate. So our cation, that's Na+, and our anion is HCO2-. So in this case, sodium, it should be immediately apparent that sodium is the counterion of a strong base, because sodium hydroxide is like the most famous strong base in existence. And so since this is the counterion of a strong base, this is going to be neutral. Now HCO2-, that's our anion. So the question is this anion the conjugate base of a strong acid or the conjugate base of a weak acid? So formic acid, the conjugate acid of HCO2-, is that strong or weak? Well, if you looked it up in your reference tables, you would find that formic acid is a weak acid. So that means that the conjugate base of a weak acid is itself going to behave as a weak base, right? And so since we have a neutral cation and a weakly basic anion, that means that our solution is going to be basic, folks. All right. And for this last one, I just realized that I'm taking up way too much room, so I'm going to move myself. Where am I going to move myself? I'll just move myself in the top middle there. I think I can be out of the way there. All right. So the last one is this NH4F. That's ammonium fluoride, right? So what is our cation going to be? It's going to be NH4+, and our anion, that's going to be F-. So NH4+, is that a counterion of a strong base? No. Is that a small, highly charged metal? No. Well, that looks a lot to me like it's the conjugate acid of a weak base. So since it's the conjugate acid of a weak base, this cation is going to be weakly acidic. So this NH4+ behaves as a weak acid. Now F-, well, that's the conjugate base of HF, hydrofluoric acid. So the question is hydrofluoric acid a strong base or a weak base? And again, if you look it up in your reference table, you will find that HF, hydrofluoric acid, is a weak base. So since our anion is the conjugate base of a, did I say base? I meant acid. HF is a weak acid. So since our anion, F-, is the conjugate base of a weak acid, F- is going to act as a weak base, right? And so we have a cation, which is weakly acidic. We have an anion, which is weakly basic. And so our solution, well, we would have to look up the numbers. We would have to look up the relative values of Ka for the reaction of ammonium ion, NH4+ with water, and Kb for fluoride ion, F- with water, to be able to figure out whether that solution is acidic or basic. So I'm just going to do a little question mark over here, right? I don't know. It just depends, right? Now, if you guys want to see a practice problem at some point in which we solve a problem like that, if we have an anion that's weakly acidic, or excuse me, a cation that's weakly acidic and an anion that's weakly basic, and we want to know what the pH of that solution is going to be, whether it's going to be acidic or basic. We can go through a problem like that if anybody is interested, but it's pretty straightforward. You just look up the values of Ka for the acid and Kb for the base. Whichever one's bigger is going to dominate, right? So if the Ka is bigger, then it'll be an acidic solution. If the Kb is bigger than the Ka, then you'll have a basic solution. So, all right, there you have it, everybody. That was the acid-base properties of ions and salts. So I hope this video has been very, very helpful for you. I hope it's at least been somewhat helpful for you. Like I said at the beginning of this presentation, I think this stream and one more next week will have us completely covering the topic of acids and bases. As I said before, also, please leave me your feedback. I read every comment. I try to respond to every comment. If you want to support the stream, giving the video a thumbs up or donating some other way would also be highly appreciated. So, all right, everybody, that's going to do it. I hope you have had a wonderful weekend, and I hope you are geared up to have an amazing, awesome, wonderful, productive week. All right. Take care, everybody.